Okay, let's talk about bypass capacitors. Bypass capacitors are probably a subject you haven't been taught or talked about a lot. We're going to place some capacitors on our board to help regulate our power supply and keep things clean. Let's go back to our libraries, back to miscellaneous devices, and when we get there we'll see we have several different types of capacitors available here. All different types. Alright, I'm going to place some capacitors. You'll see this capacitor, miscellaneous capacitor, has two parallel lines to describe a capacitor as a schematic. We can come down to the capacitor polarized and you'll see a straight line and a curved line with a plus symbol to show that this capacitor is polarized, meaning it must remain positive here relative to here. Alright, this point must always be a higher voltage than here. So let's place a capacitor. I'm going to highlight the cap. I'm going to tell it place cap. Before I place the cap, my same old trick, I hit the tab button. I don't want to see where it says cap. And I don't want 100 picofarads. I want 100 nanofarads. Okay, so I'm going to place, let's see, I'll put one here and one up here. I will need one here, and I will need one down here. Right click to stop placing parts. Back to libraries. I'm going to pick this polarized capacitor. I'm going to tell it to place the capacitor. Hit my tab key. It's not 100 picofarads. I want 100 microfarads. So I'm going to say microfarad. And I don't want to see where it says cap polarized. And I'll put one here and one up here. Right click to stop placements. I'll save. I'll go to Tools, Annotate Schematics Quietly. I want to get rid of my little red lines because I have 6 caps that don't have designators. It tells me there's 6 things that need to be updated. I update them. I'll save again for safety's sake. And now I see I have 100 microfarad, 100 nanofarad, 100 microfarad, 100 nanofarad, and a couple of 100 nanofarads waiting for me down here. Let's wire these up. First thing I'm going to do is I'm going to move these. I drew a box around those two. Move them over a little bit. I'll draw a box around this. And I'll move it over a little bit. Maybe right there. And I'll draw a box around these two. And I'll place them. Now let me move my net. You'll see what I'm doing as I go along. I'm going to draw a nice power supply. Come up here to my toolbar and get my place wire. Click to here. Click to here. I'll click all the way across here. And from here to here. Alright, I'm going to right click to stop wiring. Lift up my net. I'll move this net. Get my wiring tool again. You see how I'm wiring these up. And I'm going to come up to my toolbar, grab my ground, place my ground, place my ground, and I have my inputs wired, my power supply input wired with 100 nanofarad, 100 microfarad, both sides of my rail, positive and negative. And I have plus 12 volts with 100 nanofarads on the input, minus 12 volts at 100 nanofarad on this input. Now let's talk a little bit about why we'd want to do this. 100 microfarads in parallel with 100 nanofarads. 100 nanofarads is the same as 0.1 microfarad. I now have 100.1 microfarads. That's only a 0.1% increase. Not really worth much, right? I mean, why would we want to do that? Same on this side. Then I have this in parallel, 12 volts DC right here, parallel. So now I have 100.2 microfarads. Doesn't make a lot of sense, but let's talk about why. And the reasons why is because of the physical attributes of these capacitors and the electrical attributes. One of the biggest reasons we do this is, first of all, my power supply connections, I have no guarantee where my power is coming from. I don't know if it's clean. I don't know how long the wire is that feeds this. So I'm going to put a big capacitor here because this large 100 microfarad capacitor can store a large charge. The disadvantage of this electrolytic capacitor is it has a higher ESR, and ESR is equivalent series resistance. It's like having a resistor in series right here on this capacitor. So this capacitor can hold a lot of charge, it just can't move it real fast. The advantage is it's inexpensive. These capacitors in bulk, when you make a big project, they might cost you a nickel. This 100 nanofarad is a ceramic capacitor. Now, this electrolytic is made with two long, narrow strips of aluminum foil with an insulator in between them, and they roll it up real tight with electrolytic and like a special liquid they put in there called electrolytic. And once you put that together and roll it up real tight, it's physically small with a large capacitance. Problem is that long strip of aluminum, it has an equivalent series resistance, right? It has a DC resistance. It also has some inductance because it's a long strip of metal. That inductance is no problem at DC. It's a little bit of problem at high frequencies. This ceramic capacitor is made with a little ceramic disc. I mean, if you made a big one, it would look like a coin made out of ceramic, a little flat disc. They plate metal on both sides of the disc, and then they hook leads to those plates, the plating on the metal. That gives you a small area where this capacitor gives you a large surface area. This gives you a small surface area. But this little capacitor here has a very low ESR. It can dump its current very quickly. It can't hold a lot, but it can dump it quickly. Now this little capacitor, it might also cost you a nickel in quantity. The problem is these ceramic caps, if I wanted to get 100 microfarads in ceramic, probably cost me $15, maybe $18. They're expensive. Expensive to get very large. So the trick is to put them in parallel. I have 100 microfarads, give me a lot of charge over the long run. 100 nanofarads, I can dump current quickly when there's a power spike. I put the two together, I get the best of both worlds. Now I have another 100 nanofarads over here. Why would I have this one over here? Well, let's look at an example PCB, and it'll explain a little bit of why we do that. I'm going to open up this printed circuit board here and show you. Here's a transformer, here's a bridge rectifier, and here's a regulator. This little regulator is going to put out a 15-volt supply. So everywhere you see this white line, and you'll see my mouse is following it, is 15 volts. And you'll see that little trace. It's only 10 mils. That's 10 thousandths of an inch wide. Here it comes. Comes down here. Comes over here. Comes over here. Now it's going all the way across the board again. Comes way over here. Comes down here. Keeps going all the way across the board again, all the way to here. So now I have a long, thin piece of copper feeding the power to all my components on this board. Now remember, Ohm's law works for mega ohms. It also works for milliohms. When I look at this long, thin little piece of copper wire, it has a DC resistance. As I draw current, the farther along I go, the lower my voltage will drop. As well as, that's about 3 feet or so of trace, I'm going to have some inductance. So way at the end, down here, when this little active part down here decides it needs a current pulse to do its job, maybe there's a very fast signal coming in, there's a current pulse, I'm going to have too much inductance to maintain my supply voltage here. I'll have a drop in the voltage. What can I do to stop that drop in the voltage? I put a bypass cap, and lo and behold, look what's right here. A bypass cap. And where is it? Right next to that active component. Look, here's another active component, another bypass cap. Another active component, another bypass cap. It's a smart engineering idea on most designs to put a bypass cap right next to every active component on your circuit board. And as you can see on this board, they have bypass caps on every active component because I have to deal with the inductance and the DC resistance of this trace all along the entire board. So as I look back at our little op amp we're building here, our little amplifier board, I have bypass caps here to protect myself from what's coming in from the external power supply. I don't know what it is, so I want to clean it up here. This will give me a surge current that's slower. This will take care of surges that are fast. And then I have bypass caps right next to the op amp to help take care of the problems of long traces moving all over the board from the power supply. I hope this helps you understand bypass caps, and remember, this is your board, your artwork, your design. You want everything to be nice and clean. Use bypass caps. Thanks.